As we push faster and higher toward aerospace superiority, each part of a weapon becomes more specialized. The Air Force calls for an integrated design approach to each weapon system. And so, many elements are developed specifically for one air vehicle. However, greater demands on the air crew call for ever closer relationships between man and machine. Instruments, therefore, have been a major exception to the weapon system concept, seldom designed specifically for any one weapon system. Perhaps the most important reason why most instruments are standard Air Force items is training. Imagine the confusion if a pilot faced a completely different panel each time he changed aircraft. Imagine some vital split second while the pilot adjusted himself to some new reaction from an unfamiliar instrument. Under the Air Force Integrated Panel Program, pilots will find generally a new look in instruments, but with a real consistency among aircraft. Pilots need the best balance between the specialized panel, which fits only one model of aircraft, and the rigidly standardized panels, which fit all aircraft but don't really do the job on any of them. They'll find that balance when elements of display and control are integrated with aircraft subsystems under the principles of the whole panel concept. In the design of the panel and flight control subsystem, weapon system contractors will establish procedures to ensure that all aircraft subsystems are linked effectively with panel displays and controls, so the flight crew can carry out the assigned missions in the safest, most effective manner. Imagine a weapon system contractor designing a panel subsystem for a completely new weapon. It could be a manned orbital space bomber. It could be the mobile flight control station of a missile system. It happens to be a fighter bomber. To examine the problem of display and control design of a typical weapon system, we'll visualize a completed aircraft like this, but only for purposes of discussing procedures. We'll look at three major categories of effort and hear from the man who heads each function. Operational analysis. What must the weapon do? Display engineering. What must the crew see and control? Systems integration. How can each subsystem be matched to all other subsystems? Let's begin with operational analysis, for the panel and control design will be governed by the missions, more so now than ever before. Let's hear from the contractor's Mr. Operational Analysis.
I suppose there isn't any specific point where you can say our work in operational analysis begins. In study phases, we work from definitions of general missions and tactics. For this fighter bomber, our operations people are trying to predict the detailed operational conditions, considering many factors, including friendly and enemy electronic ground environments. You are all familiar with mission profiles, showing such factors against altitude-distance relationships. Our effort must be closely coordinated with what we call the Systems Integration Group, which is establishing requirements for guidance and control subsystems.
Our work in systems integration includes the assembly of information on flight control equipment to fit the requirements of the weapon system missions. We have to determine the types of subsystems and from each subsystem the required function output. The selection of types of flight control equipment is an important factor in the crew function studies based on the mission analyses.
In operational analysis, our human factors people examine each mission profile, translating it from a base of miles to a base of minutes. We want to examine crew responsibilities at each minute, a task analysis. In some cases, we will examine the mission second by second, as for example, the takeoff. Watch how quickly things happen here. Second-by-second analysis of crew responsibilities is required during some flight phases. Longer analysis intervals are used on other phases where the requirements are essentially constant for longer time periods. We keep alert for phases such as the attack, where perhaps too many things must happen at once. Operational analysis uses every means possible to simulate missions and to perform tests so we can recommend which function should be automatic, which function should be manual, and which ones at the pilot's option should have both automatic and manual control. Such analysis considers many features. Our overall consideration is that the flight crew is superior to machines to carry out operations demanding motor skills, to recognize and interpret complex patterns, and to maintain flexibility of decision. While we work on the crew function study, we supply detailed analyses of the aircraft missions, including three-dimensional mission models, to the systems integration people.
By this time, systems integration has a preliminary schematic drawing of the flight control system. We consider the mission according to subsystem rather than flight phase. This is takeoff flight phase, climb flight phase, followed by cruise, descent for the attack, penetration to the target, and so on. But when we consider the subsystem which is providing guidance information to displays and to the autopilot, we see that a TACAN system governs this portion of the flight. So the climb and a portion of the cruise would be in a TACAN mode. We see that another portion of the cruise and this descent penetration are another mode, in this case inertial. The whole mission is analyzed this way. In this area, data link controls the recovery and return to base by systems such as VolScan. The final mission phase is approach and landing, perhaps in an ILS mode. So this, combined with timeline operations analysis, gives us a good basis for our study of what the crew must see and do. This determines the signals that must be supplied to display and flight control. We examine how signals can combine for adequate guidance and how the displays can show the output of combined subsystems. From this kind of study, we make up a flight mode analysis chart. We consider each element of display, such as Mach, IAS, safe speed, G, on down through, altitude, heading, course, and so forth. We also examine automatic flight control system references. What is the origin of the signal that will drive each element of display and or furnish a command to the autopilot during each mission phase? From such a chart, we can see, for example, that the bank steer needle might receive inputs from the inertial system through the flight director during the penetration to target. But the same display element should also receive inputs from the terrain clearance system for part of the time. The autopilot may need similar combining of signals from more than one subsystem. We determine all combinations of information sources and how certain signals must be changed or combined for adequate guidance. We can also see the elements of integrated display as they will be used by the air crew. When we complete this chart, it becomes, in effect, the summary of control display needs. At this point, we begin to work even more closely with the display engineering group.
In our display engineering effort, we are studying the nature of the information required by the crew to carry out the specific functions established in the mission analyses.
Working with the systems integration people, we study the flight mode analyses to see where existing or developmental displays may not be adequate for use in our weapon system. Display development is in accordance with the whole panel philosophy. Our guide is WADC Tech Report number 56-582. We look for improvements consistent with the state-of-the-art advancement. We recommend new display developments only when they are clearly needed to complete the mission. For example, terrain clearance display is required for the low-level portions of our mission. Perhaps this radar display becomes a part of the flight control system. The pilot may place a PIP on the desired flight path so the flight control system can maneuver the aircraft for the best terrain clearance flight. These are things we must study. When we have considered each element of display and flight control in terms of mission function requirements, we prepare a detailed program for development of displays within the time requirements of the overall weapon system development program.